Vibration analysis and design of post-tensioned and RC floors. The outline of this presentation starts by explaining why are we concerned about vibration. Specifically, when it comes to post-tensioning, I jump ahead here and say post-tensioned slabs are typically thinner than their equivalent RC slabs, and that makes them prone to vibration more. That is one thing. And secondly, the advent of computer programs in analysis and design has enabled a lot of architects come up with larger spans, irregular layout, aspirational geometries, which make them at times more prone to vibration. For that reason, the vibration analysis, and for the other reasons that I will just be explaining, become more important. Now, what are the causes of vibration? What are the allowable limits of vibration? How to evaluate the vibration for its acceptability? How to control it if it is not acceptable? Go through a numerical example, and then go through alternative method of vibration analysis. The numerical example would be based on common state of knowledge. The alternative is based on prior state of knowledge, maybe 50 years ago, 60 years ago, when computer programs were not as widespread as they are today. And then I will also go through the example of the alternative method. That would be helpful for those of you who may not have access to specialized software. Then we talk about post-tensioning, effect of post-tensioning, effect of cracks in concrete, and before closing, rhythmic vibration, like dance halls, exercise rooms. They have their own criteria. And finally, the impact of vibration on sensitive equipments, laboratories. Close it with references. Now, why are we concerned about vibration? Because vibration may be annoying by occupants. Then we need to know what is the threshold of perception. You have to perceive it before you become annoyed. And what is the threshold? What makes you annoyed? Vibration may also interfere with proper function of equipment and instrument, which is a different story. We will talk about it at the end of this presentation. Let us concentrate on perception. Perception of vibration depends on frequency of it, which is cycles per second, and peak acceleration, which is expressed as percentage of gravitational force by acceleration up and down movement, acceleration from up and down movement, the maximum acceleration for up and down movement. Now, frequency is defined by cycles per second. Acceleration is defined for vibration analysis as a percentage of gravitational acceleration. This is the chart which is commonly, let us go back. Let us, Now, without my glasses, I might not be able to read it. Okay, good. That sounds better, looks better. Now, this is the chart that is commonly used. Now, in this chart, here you have the peak acceleration as percentage of gravity, and here you have frequency. That means 4 cycles per second, 8 cycles per second. Here is 0.5 gravitational acceleration. For common residency and office, this is the chart. If the floor vibrates at 4 cycles per second, then the perception level will be around 0.5 of gravitational. For hospital rooms, operation rooms will be different. Obviously, the level of acceptance is more strict, is less. This is 1, this is less. Remember this number 1, because later we will be looking at another chart that will have around 10 for its ordinate. This is about 1. So it is the lower part of the general chart, the bottom part of the general chart. Now, there are 6 steps that you follow for evaluation of a floor's vibration. Step number 1, you determine the natural frequency of the floor. The natural frequency depends on the geometry and material properties, boundary conditions of the floor. That is property of the structure. That is a structural matter. Then select the exciting force. What is it that causes vibration? Third, what type of floor you are dealing with, the specific location that you're interested, what type is it, its thickness, material properties, and so on. Then we calculate the weight of the floor that we are concerned about, because the weight has to go up and down, would be a parameter in vibration analysis. Then number 5, we calculate the acceleration, peak acceleration caused, and then evaluate it. By evaluation, I mean we go to the chart that we looked a little while back to see whether it is acceptable or not. Now let us look at this example. Here, let us assume that your office is somewhere here, and somebody is walking. The most common case is footfall as a result of people walking on the floor, whether there will be vibration which is perceived and is not acceptable. Now, let us assume that you have an office here and this is the floor. You have to determine its frequency. You use a program today which is based on plate elements. Plate elements in bending doesn't have to be flat shell element, just bending will do. A finite element with bending plate formulation. You go define the specific parameters of the floor, such as whether it's operating room and so on. Then you observe the modes of vibration from the program. The program gives you the modes of vibration, and then you select the mode that is dominant as far as your location of concern is important. Here I have the floor shown. Use a software in this case I've used our own software, Adapt, that is now RISA. The first mode shows vibration here. This is not where my office is. Then the second mode shows vibration, the peak here. The third mode shows here. So after you determine the natural frequencies, you must also look at the mode shapes. And do not select necessarily the first frequency. You select the frequency that is associated with the mode that vibrates the location of your interest. So in this case, mode 5, actually, this is not mode 3, I see it's mode 5. I skipped from 2 to 5 here to save space here. This is mode 5, which is of interest for my concern. I have to note the frequency associated with this mode. Then we go to exciting force. That is step number 2. What is it which is causing a vibration? The most common case is footfall. Footfall. As individuals walk, there will be force exerted on the floor. Now, this is the frequency of steps, how many steps per second an individual takes, and this is the percentage of the weight of the individual, or rather than percentage, I should say this is the fraction of the weight of the individual who is walking. So if somebody walks at 2 steps per second, about maybe a little bit over 50% of her weight will be acting as exciting force on the floor. So use graph shown. Exciting force is a dynamic load factor times the weight of the person. Then step number 3, you estimate the damping factor of the floor. In other words, depending on how the floor is furnished, it may dampen, reduce the impact of vibration. For that, we refer to the following table to select the damping factor beta. Typically, it is 0.03, and the recommended values vary between 2 and 3% for bare concrete and 5 to 8% for furnished rooms. So for office buildings, moderate furniture, it is 3%. So we assume that there is some furniture and it will not be 5. It will be 3%. So we assume 3% in this case. Step number 5. What is the peak acceleration resulting from footfall? We use this empirical formula. This is the acceleration, peak acceleration, gravitational acceleration. So this is peak acceleration in terms of a fraction of a gravitational. This is the force of the individual. This is the frequency. This is the damping factor. And W is the weight of the floor. And these are all explained down in here. W is the effective weight of the panel and the superimposed load. If the superimposed load is attached to the floor in a manner that it goes up and down with the vibration of the floor. And G, we assume 32.2 foot per second square. Step number 6, we go and evaluate the vibration impact using the chart that we looked at a little while ago. We use the natural frequency from step number 1, peak acceleration from step number 5, and use this chart. This is how it works. Let's go through a numerical example. Let us look at this floor, and let us assume that we are interested in the vibration here, this panel here. I have the properties of this floor given here. It's concrete slab thickness, dead load, concrete strength, modulus of elasticity. Now here, I like to draw your attention to this 1.2 factor. What I want to say is for vibration, the modulus of elasticity is increased by 20%. It is different from modulus of elasticity for static loading. So we multiply it by 1.2. What is required is to evaluate vibration compliance of the floor that is going to be identified. This is the panel that we want to check. This is the panel. I have its dimensions down here. You use a finite element program or any other program which gives you the frequency in addition to mode shape, because from the several frequencies you select the one which excites the location of your interest. So I determine the frequencies as step number 1, create a model, assume modulus of elasticity 1.2 times the static, include weight of the objects that are attached to the floor and they go up and down with the floor, and obtain the first few natural frequencies. This is again the plan, and I see this is the first mode. It vibrates here. This is the second mode, definitely of not interest because the maximum is farther away from place of interest. The third mode excites this here. So it seems that in this case, this one is going to, the first one is going to be the mode of interest for me. Then what is the exciting force? That is step number 2. I assume an individual walking on the floor. The weight of the individual, I have assumed 150 pounds. Reasonable. Today, maybe the average weight might be more, but that's 150 pounds, which is 667 newtons. Assume that the individual walks 2 steps per second. Then I come here, 2 steps per second. It will give me this dynamic load factor, which is 0.53 from here, multiplied by the weight of the individual to find the exciting force. Then what type of floor are we dealing with? This is an image of an office building. I assume a floor like what you see in the image, and 0.03 will be its damping factor. Then I have to calculate the weight of the floor, the weight of this panel. For the weight of the panel, I assume 20 pounds per square foot as partitions that are attached to the floor, and go up and down, or cover of the floor that goes up and down. So concrete weight is this. I have the slab thickness, which is 8-inch, and this is the superimposed load. I have the dimensions of the floor, so that should be 26 and multiplied by, this point is multiplied by here. That should be 26.3 multiplied by. So the weight is this. That is the weight of the entire panel. Next, I go to peak acceleration from step 5. The formula that is commonly used is this. In this formula, we looked at it before, I have the peak acceleration as ratio of gravitational acceleration. These are the parameters that I calculated. That was the frequency. I substitute these in here. I substitute and I find 0.37% of the gravitational to be the peak acceleration. 0.37%. Then I go to step number 6, which to evaluate the outcome. I use the frequency selected, peak acceleration calculated, come here, this is the frequency selected, and this is the peak acceleration selected, and I see that this panel is okay for office and residence. It falls below here. But it is not okay if we have an operating room in a hospital. To make it acceptable for operating room, I have to bring this further down. So it is okay. Now, this presentation that I outlined, I'm surprised, all in the middle, this should have been one of the first slides. This is what I covered. Now I'm moving to part 2. Part 2 was definition of the phenomenon and how what is the cause of vibration and how you will evaluate it if you use a commercial program. Part 2 is going through the same, but assumes that you don't have access to a computer program. And in the past, when computer programs were not available, the problem existed, vibration problem existed. So engineers were using alternative methods. And this is what I'm going to do here. This is what I'm going to do. There were a number of tables available like this one here, which are taken from the literature. I have the reference where I got this table. You use the traditional method where it gives you a panel with different boundary conditions. The double line means fixed or continuous. Single line means edge of the slab. For example, in this one, this is a panel along the edge on 3 sides continuous. For this panel, its vibration frequency can be approximated by this formula. And you come here and you estimate the natural frequency of the floor using empirical table like the one I have here. You read the parameters associated with the boundary condition, and obviously you may have to make some engineering judgment regarding the shape of the mode. We will get to that shortly. Good. Then you read the formula associated with the panel you selected, and based on the aspect ratio, you calculate this constant, phi. And you bring the constant here, you calculate the frequency. We are after frequency. This is the span. C is a constant, which depends on other elements that come into the picture. C relates on the modulus of elasticity, slab thickness, load, Poisson's ratio, and so on. The parameters are given here. Once you have the value of constant C for the panel, you find the frequency, and then the rest of it is like what we had before. Now, when you use this traditional method, you have to be aware of this, which mode you select. Shape of the first natural frequency, the first mode of vibration is affine to that of a single panel simply supported. The first mode looks like this, as if it is simply supported, not analogous to the deflected profile under self-weight. You see, the deflected profile is like this, but the first mode for a single span is like this. Now, the two are somewhat different. Let us see. Use simply supported boundary conditions along the four sides of an interior panel. If you have an interior panel, you can assume the vibration is like this. It will be like this, simply supported. That is, if it is fixed on the sides. Where columns are on a regular or orthogonal grid, the first mode is likely to be in form of a one-way slab deflecting in a cylindrical form. So this is how the first mode is going to look like that, if they are on, so to say, regular supports. Panels bounded by smaller spans may act more like fixed. If the next span is small, it might act more in this fashion. Now, I'm going to go through the same example, but use the traditional method. To use the traditional method, for the first mode, I have to assume a shape of vibration to go to that table, which we had in the previous slide. I assume that the shape of vibration is going down all here and coming up all there. That is how, in fact, that is very likely to be the case, a little bit different from what we assumed in reality, but for first assumption, if you don't have a program, that would be a reasonable assumption. So for that shape, I will use calculate C. Remember, we use to calculate phi from the table and come and calculate C, which is the constant properties of that panel. And the properties of the panel are given by its load, modulus of elasticity, thickness, and so on. I have these all written here. For modulus of elasticity, I have used 1.2 times the elastic. So this is the item I have selected from the table. That is the value of phi, and C constant is this, and I get the frequency from this formula where phi comes from here, C comes from here, and A comes from the panel span. I have taken this whole length, 3 panels to go down and 3 panels to come up. Whether you assume 1 panel or 2 panels or 3 panels, you will find out as long as it is all in cylindrical geometry, the answer will be the same. 1 span, 2 or 3, all will give the same frequency if the shape is the same. The length doesn't matter. Now, can I get this out of the way? Let us see. Maybe here would be a good place. Good. So here I have found the frequency to be 5.59 Hertz. Not far from what I had before. I use the same formula for peak acceleration. And the peak acceleration is 0.4, somewhat different from what I had before. I use the frequency and the peak acceleration and go and see this time the outcome is here. Remembering or observing that the entire range here is acceptable lends me to believe that the outcome being a little bit down or up is not going to impact the conclusion of the analysis. So the analysis need not to be very accurate because it is a decision whether it is above or below of a threshold. How much below it is or how much above does not, in this instance, make a difference in the final conclusion. It is acceptable for office and residential, but not for operating rooms. This is operating rooms. So this was part 2 of this presentation, which was repetition of part 1 for the condition, for the case that you do not have access to a software and then you use the traditional method of design, the old method of design. Now, we covered part 1, I covered part 2. Part 3 of this presentation explains impact of post-tensioning and cracking of concrete. Post-tensioning slabs are thinner than their conventionally reinforced concrete. Hence, they have lower frequencies. Pre-compression from post-tensioning inhibits or reduces crack formation. Post-tension slabs are stiffer than RC, stiffer because of not being cracked. That is the reason. Otherwise, the stiffness is the same if RC doesn't crack. RC slabs of the same thickness, they are stiffer than RC slabs of the same thickness on account of having less cracks, hence higher frequency compared to RC of the same thickness. The other item that is also referred to the literature, sometimes with a different conclusion than what I am going to present here, is this, that post-tensioning imparts axial compression if it is at the centroid, not moment. Axial force from external sources result in P delta moment, reduces the bending stiffness. If you have a post-tension, if you have a concrete member, you put axial force and then it vibrates. As it goes down, there is a force times displacement P delta, which will reduce the stiffness of the slab. Some literature refer to post-tensioned members having less stiffness in vibration because of P delta. Here, the objective of this slide is to emphasize that P delta effect doesn't exist for post-tensioned members because internal post-tension forces not cause P delta moment, because the post-tensioning is here contained within the body of the concrete. As the member deflects down or up, the eccentricity of the post-tensioning with respect to the cross-section remains unchanged. Here, the eccentricity changes. That is why you develop a bending moment. You do not develop a bending moment because of deflection. Likewise, even if it is externally post-tension, when the member goes down, the eccentricity of this force with respect to the centroid remains unchanged. For that reason, you can have precast, pre-stressed piles that are 100 feet, 30 meters or so, and they are lifted by a crane to go to place of installation and bend, but they do not break because the pre-compression, and they have very high pre-compression, by the way, much larger than slabs for gravity design, 3-4 times more pre-compression. There is no P delta, even though the pile might bend visibly greatly. So that is as far as P delta is concerned. What about cracks? If you have cracks, the applied moment doesn't change from external load, but cracks reduce the moment of inertia. Reduction in moment of inertia locally results in change of stiffness, and therefore there will be a change in frequency. The reduction in second moment of area results in reduction in frequency. Figure B here shows the demand moment. Demand moment doesn't change based on geometry and load to be resisted by the reduced moment of inertia. That is why you end up with a reduction. But if you wish, the software can calculate the initiation of cracking and the extent of cracking. What you see at the top here shows the reduction of stiffness due to cracking from application of self-weight and superimposed load. Here, now let us see again, move this out of the way. Oh, good. Here, for example, for bending moments about the vertical axis, the reduction of stiffness is a maximum of 31%. In other words, the stiffness is reduced to 31% because of cracking in one direction and the cracking in the other direction. And the software gives you the frequency accounting for the extent of cracking under the self-weight and other loads that you may have. So cracking is something that you can account for if you wanted. Available software permits. So what did we cover? Part 1 of this presentation defined the requirements and used software to do the analysis. Part 2 used the previous fashion of a semi-empirical table. Part 3 talked about post-tensioning and cracking. Now the last part. The last part talks about rhythmic motion, dance hall, aerobics, and laboratories where you have sensitive equipment where other considerations apply. Now, rhythmic motion and dance or aerobics, the determination of the floor's vibration is the same as the common condition described earlier. In other words, frequency is property of the floor, its supports and material properties. It is the impact of the vibration on the people that will be different this time. Exciting force of the human activity and the tolerance will be higher. Exciting force will be also different. Previously, we had walking. But if you have a dance hall or aerobics, then exciting force will be more. There are two things. Exciting force is more, tolerance is also higher. This is the table commonly used, and in this table we have, for example, if you have dancing, the force frequency is typically this range, but we will calculate it. This is just from the reference. The weight which will be considered is given here on this assumption that each couple is likely to occupy so many square feet, and depending on the average weight of the individuals, so the force will be more depending on the denseness of the people. So the dynamic load factor will be again a different value here, and the total dynamic load intensity given by this will be this much. These are the force times area. This will be the force, pound per square foot, which is based, that pound per square foot is based on likelihood of how many individuals are going to be on a dance floor, therefore what will be the pound per square foot. So this is important, and if there is a concert hall or a sports event, the likelihood of a load per square foot is this, and aerobics, the likelihood is being this. Probably there will be a larger distance between individuals in this type of activity, so the intensity will be less. And these are the areas that are assumed for occupancy of people in these events. So step number 1, the exciting force is now different from before. You have a higher exciting force depending on the activity. This is step number 1. And if we go to the same numerical example and evaluate this for a dancing, the frequency is the same. Frequency has nothing to do with the applied load here. The exciting force now is a little bit more than before. We had less the exciting forces, and then this is the total force. The damping factor is the same, and the total weight of the floor will be this. We calculate the peak acceleration using the same formula. This is the same formula that we had before for peak acceleration. This time it is 18.4%. I remember last time we had the peak acceleration something about 4. And with that calculated, now I move this image. Now it takes a little while to recover. Let's see. Okay, that is the peak acceleration. Let us move it out. This is the same formula. Good. I go to the evaluation chart. Remember, the first similar chart we looked at had 1 as its highest number. This has 10. So it is much higher than the previous one. The previous one we looked at will be down here, which falls off. So we evaluate the outcome using this chart, which gives us a much larger tolerance. Frequency is unchanged, but peak acceleration this time has changed, 18.4. The other time I think was 4 or something. Now, note that the threshold of acceptable peak acceleration is about 10. That is 10% of gravity, that's what it is. More than what we had before. With 10% being the maximum, the sensitivity diagram clearly indicates that the calculated 18.4% is not acceptable. What we calculated was 18.4, whereas 10 is acceptable. So the floor that we have is not good for dancing. It will vibrate too much. We have to do something. We may increase the slab thickness to 11 to 80 millimeter, 11 inches. Before it was 8 inches. If you increase the slab thickness, the frequency will have to be recalculated. This will be the frequency. The weight will be different. Now the weight is more. And the peak acceleration will be 4.9, which is much lower. Here is the peak acceleration. So the chart indicates that increase in thickness makes the floor suitable for rhythmic activities. Now we move into another question, and what is the impact of vibration on sensitive equipment like laboratories? The National Institutes of Health has a table which says the sensitive equipment, the vibration from sensitive equipment is measured by velocity of vibration. Before, for humans, we had the acceleration to determine whether it is acceptable to individuals. But when it comes to equipment, it is the velocity. For example, in this table, which is coming from the National Institutes of Health recommendation, if you have a bench scope up to 100 magnification, the maximum velocity should not be more than 50 micrometers per second, and the maximum given in maximum velocity expressed in micro inches per second. This is in metric unit. This is in MIP, MIP micro inch per second. It will be for this scope 2000 MIPS micro inch per second. So that is what you have to do to evaluate whether the floor is good for specific equipment that is going to be positioned in it. The equipment rating is expressed in terms of micro inch per second, MIPS, or micrometers per second. Table lists the recommended values given by institutes of health. Everything remains unchanged. The first 5 steps remain unchanged. So in the 6 steps are the same. Now in step number 5, rather than calculating the acceleration, you have to calculate the velocity. Everything else is the same. So step 1, you determine the natural frequency. Step 2, you go to select the exciting force. It could be footfall or whatever. Step 3, calculate floor type, then weight of the vibrating panel. Step 5 now. Step 5 is going to be different. Before we calculated the maximum acceleration, here we are calculating the maximum velocity and then go to evaluation. The maximum velocity uses this formula, in which, again, this is the weight of the floor. This is the exciting force, which could be the same as for regular. Gravitational acceleration, that is damping. This is the weight of the floor, and that is the frequency. Now, if you go back to the same example, determine the adequacy of the floor for footfall, for general, as a result of footfall, for general laboratory. Frequency doesn't change. That's what we calculated before. Exciting force in this case doesn't change. It is the same individual walking. Damping factor the same. Weight of the floor the same. So the only thing is now we calculate the velocity. We use the parameters we had before in the velocity formula, and that is the velocity we find inches per second, which is 17,000 MIPS, micro inches per second. So we go to evaluate it for the floor, 17,000. For evaluation, the response of the floor, 17,000 MIPS, is larger than what is in the table 17,000. Now I forget which one we had, a bench microscope or something. It is definitely larger than all these. So it's not going to work. 17,000 is much larger than what is permissible. So you have to do something. We can increase the slab thickness. That is one option, from 8 inches to 12 inches. If we So if we increase it with the 12 inches, the velocity will become acceptable within the range. Good, and these are the references which were used in generating this presentation. In summary, Part 1 was definition of what causes and what is acceptable, and we used a software to determine and evaluate an example. Part 2, we used the same definition, but rather than using software, we used empirical relationship. Part 3, we talked about impact of forced tensioning and cracking of concrete. Part 4, the last part, we discussed acceptability of vibration due to dance, aerobics, rhythmic motion, and also on equipment, laboratories, where the equipment could be sensitive to vibration. Very good. Thank you for listening. Additional information is provided in the book reference shown on the right. Thank you.